Thank you, everyone. Okay, the only problem with this is gonna magnify all my sneezes and everything, so I apologize for that. Thank you very much. It's a great pleasure to be here. It's a great venue, and I really appreciate all of you coming here, staying inside rather than staying outside. So my name is Pinki Mondal. I'm an assistant professor at the University of Delaware, and today I'm going to present some work that I did with a collaborator at New York University and my master's student at the University of Delaware. So I just wanted to talk a little bit about the study areas. So I put this mandatory study area slide up front because I wanted to let you know that we are focusing on 6 South Asian countries, as you can see here, because this region hosts 23% of global population and spans over only 3% of land area. So just think about that number and try to anticipate what kind of pressure we would see in that area. So what we are looking at here, all the different forest types in South Asia, these South Asian countries, coming from broadleaf or needle-leaf forest, evergreen deciduous, mixed forest, savanna, and sometimes we also see some trees which are kind of dispersed in between croplands. We do see a lot of croplands flanked by trees. So if there are enough trees, we have considered that as a fragmented forest for this study. So looking at the SDG, the Sustainable Development Goal indicators, specifically 15.1.1 and 15.1.2, forest area and percent protected areas, those are the 2 SDG indicators that we will be discussing. However, what we would like to argue here that we need to go a step beyond that and not just think about forest area and percent of protected areas. The reason being that if you look at this graph showing for 6 countries, you will see that in the bottom panel, percent of land area, forest area, has been kind of stagnated over time for most of these countries. If you look at the percent of total land area for terrestrial protected areas, that too have been kind of stagnated over time except 1 or 2 countries. And as we said, that population is only going to increase. So how does that work? So if we are just looking at forested area and protected area, I just wanted to draw your attention to this case study we have been doing in central India. All 3 figures or pictures are from the same protected area. Protected area where the forest is supposed to be intact. So even though this land is under protection, so it will be identified as protected area, and it is identified as forest land on most of the widely available datasets, global datasets. As you can see, there is obviously visibly thinned canopy here, and some places are completely deforested. So what we are trying to do in this study is to look at areas like that within protected areas and try to identify how much degradation is going on. So for this study, we identify something like this as an intact forest, something like this panel B as a non-intact forest, but still forest, and something like this panel C as a non-forest, even though it is within the protected area. However, disclaimer here, we are not trying to create another degradation index. Rather than that, we are trying to identify a consistent, simple but accurate and reproducible method to enable decision makers. So we're not talking about the scientists who obviously prefer to deal with very complicated issues, but here we are trying to enable decision makers to report SDGs, and for that we are focusing on 2 questions that I'll show you how we did that in 4 steps. In step 1, we calculated NDVI, Moody's-derived NDVI at 1 kilometer scale. We used CHIRP's rainfall data, which is 0.05 degrees, and combined them in a rain use efficiency. So it's a broad brush scale at 1 kilometer. We will come back to these figures later. I just wanted to tell you about the steps first. In step 2, we dive a little deeper, and we focused on protected areas which are showing different trends in rainfall adjusted NDVIs. So we can identify what's actually going on at a much finer spatial scale. So for that, we picked one national park, SNP in short, in India, and another national park, RNP in Sri Lanka. As you can see, they show very different trends in NDVI, very different trends in rainfall. So as a result, in RUE or rain use efficiency. Then step 3, we are looking at much finer scale when compared to 1 kilometer. We are looking at 30 meter, 15 meter, and 10 meter, because if you remember on one of the first 2 questions, we wanted to see what is that scale that where we can be still pretty accurate, but it's not too much complicated for the decision makers to do that. So what we did, we collected training samples and we did run calibration and validation as usual, nothing widely out of this world. But we ran that for both national parks at 3 different scales. And as you can see, Sentinel-2, which is 10 meter, is providing the most accurate classification. We ran a random forest classifier here on Google Earth Engine because we are looking at open resources, free satellite data. Obviously, some of you might consider using much finer level data, for example, Planet Lab data, less than 3 meter, if you can get that for an entire country like India or Sri Lanka for free. If that's not an option for you, then you might want to set for Sentinel-2, 10 meter. Now, the last part of our study is to visualize degradation within protected areas. However, since we know landscapes are complicated, every landscape, every protected area, they are different. So what we are saying, do not settle down for one method. Rather than that, you can identify different methods and then identify places of agreement or POA. So what you are seeing here, this is SNP from India, this is RNP from Sri Lanka. This is the Sentinel-2, the most accurate method that generated these classified maps, where green is intact forest and this brownish pink is the non-forest area. But what we wanted to focus on here, how these different data method combinations agree with each other. So all these orange colors, these are places of agreement for non-intact forest. So if the decision makers, they are utilizing a combination of data methods and identifying there are some areas that constantly coming up as the areas of degradation, they probably should focus there. What we found that most South Asian countries, they are witnessing localized greening and browning, no surprise there. So that's the point that if you go for a broad brush approach, 1 kilometer scale, or you can average over a national scale, this is what you'll see. You can go for a line there, but what I originally see, it's just fluctuations. And that might not be the more accurate method for the decision makers to report at a national scale. So here you see a lot of greening going on, but a lot of browning here too, especially in Sri Lanka or Western Ghats or here northeastern India. So that's the reason we are saying if you just focus at 1 kilometer level and if you just report an average number, you might gonna miss a lot of details, especially if you see a lot of greening going on within your protected area. You might not focus your resources or you might not channel your resources to better protect it. However, if you look at that at a finer scale, you might find that actually a lot is going on. Maybe there's a lot going on in terms of forest degradation. So now there are resources and there are policies and there are national level policies that might trickle down to state level or local level policies. So here we are trying to find a way that hopefully will work at many different administrative levels. It's easy enough to run, but what we argue that it's very, very important for the decision makers to run it enough times or frequently, maybe every 6 months, every year, and then come down together, maybe something like this in a room, and talk to each other where to focus their resources, if it's needed to focus their resources at certain point. Because after all, if you're reporting your SDG indicators for protected areas, and you are only reporting that all is well, that's probably might not enable us to achieve the SDG goals. So with that, I'd like to thank my collaborators, Dr. Sonali McDermott and Abdul Qadir, and I'd be happy to take any question that you have.
presentation. So I'll open the floor for questions. Go ahead.
Thank you so much, Dr. Mondal. I have one question which relates to your definitions about intact and non-intact forest and greening. Because, I mean, greening is a very vague term, if you know what I mean. And so is non-intact. Like some people define intact and non-intact in different ways. You must have read Porto's paper on this. And not all non-intact forests signal degradation.
Yep.
Especially if it's in the middle of a national park like you show Sanjay. And actually, looking at where Sanjay National Park really is, there are areas which are brown, but which are not degraded.
Right.
You know what I mean?
Right.
So I was wondering how you define intact, non-intact,
Yeah.
cleaning, browning.
That's a great question. So when we do the broad brush approach, the first stage, that's where we are trying to take out or tease apart the anthropogenic impact and the natural impact. So there are areas where it's just a natural effect, right? It's either it's warming or if it's, the rainfall is, going down over time. So we are not identifying that as a degradation, although it might go down in terms of greening. So when we are using RUE at the first level, that's where we are trying to focus on only areas where despite of increasing rainfall or cooling down, we are seeing a drop in greenness, which is basically a drop in NDVI, right? So we are masking out everything else at the very first step. Next, defining intact and non-intact, as I showed in those, obviously there's no cutoff or there's no threshold value. For this work, we defined non-intact forest as a 50% value cutoff, where visibly you can see within any pixel there's a 50% non-forest, like thinned canopy. It can be for anything. Where I showed many protected areas in South Asian context, you'll see it's because probably people are taking a shortcut, to going to their places of work. So it's a lot of anthropogenic disturbances, but it could be something else, could be some disease. So we are not differentiating between the drivers or causes of degradation here. We are just looking at if we can visibly see a thinned canopy. And for that threshold, for this study, we set it at 50%. But as I said, it's really up to the decision makers. If they think they need to set a value at 30%, 40%, they can do that. We are just trying to give a framework that is easy enough, but it's consistent enough across different ecosystems that would work, so that they don't have any excuse saying that we can run it, we don't have the human resources.
So I can take another question. Let's go ahead.
Can you give a bit more information, give us input for mapping the intact forest? I mean, that's exploratory variables.
So the intact forest is based on different satellite images. As I said, there are different bands we used for different combinations. So for one, we had Landsat 8 at 30 meter, the visible bands. Then the other, we had used a panchromatic sharpened bands for Landsat. Then the other one was Sentinel 2 10 meter. And then we collected training samples to train our random forest classifier. And we had around, I believe, over 1,000 points. We used 600 of it to train the random forest classification, like classifier, and we had 400 for validation. And if you
just use the bands, or you also use like texture indices, or
I did not use any texture index. As I mentioned that there's obviously many complicated ways of mapping it. You can get something up to 98% accurate. But here we are trying to identify the simplest method that can still give you comparable results and reproducible results. If you talk about very complicated scenarios or very complicated indices, the decision makers are more likely to say that we don't have the human power or computing resources for that. So it's not really for us scientists, because we have many indices, complicated indices, and probably more accurate way to measure degradation. But this is really for a decision maker who is sitting somewhere in a remote village in one room with a single computer and trying to identify what's going on in the landscape that they're managing.
Thank you.
Thank you.
We have to move on to the next stop. We can pick up this discussion maybe later as well. So can I invite the next speaker? Casey.
Thank you. Good afternoon, everyone. Thanks for coming. My name is Casey Ryan. I'm from the University of Edinburgh in Scotland, still in the UK, and even still in the EU, by the grace of God. If you were in the morning session, you'll probably have guessed that my talk is going to be about savannas, and it's going to be about radar data. I'm going to talk about the world's largest savanna, so prizes for guessing that it's the southern African woodlands that are a subject of this talk. Before I go any further, I should thank Ian, the postdoc in my group, who did a lot of the hard work that you're about to see, and my colleague Ed Mitchard, who I've worked on this with for many years. So I'm going to talk about these three processes: deforestation, degradation, and regrowth, which probably in descending order, we know a fair bit about deforestation, we know very little about degradation, and really not much at all about the regrowth dynamics of this system. So even deforestation, the situation's not great. If you look at national reports of deforestation rates, they're very inconsistent. They don't match up well between countries or even over time within countries. If you look at a lot of the key forest cover products or tree cover products, they're mostly designed to work well in the wet tropics. Savannas and woodlands are tree grass systems, lots of green stuff that isn't attached to wood. That really messes up optical remote sensing in these systems. And also a lot of the changes are from quite low biomass to even lower biomass, which again is a more difficult problem than spotting the kind of changes that are common in the wet tropics. So there are still some uncertainties about deforestation rates in the region. Degradation, there's no large-scale assessment, particularly of the carbon emissions associated with degradation at this scale. There are a few case studies, and we've done some, other groups have done some. But of course, if you're interested in degradation, you do a case study, you go to somewhere where there's going to be a lot of degradation. So we don't really know how widespread the kind of high rates of degradation that you see from the case studies are. And then finally, trees love to grow. If you cut them down, they come back. Particularly in savanna systems, they're very resilient. You chop them down, they grow back. This tree is coming back with 10 more stems than it started with. There's also some suggestions that global change is driving increases in woody biomass, particularly in southern Africa, but other bits of the continent as well. And the problem is that they all happen in the same 1 kilometer pixel. So you need really quite fine resolution remote sensing to tease apart the contributions of these different processes. If you look at deforestation with very coarse resolution, what you'll actually see is just a little bit of degradation if there's just a small spot of deforestation in the middle of your big pixel. So our work is trying to tease these apart, and so necessarily is at high resolution. It's based on using radar remote sensing from the Japanese space agencies ALOS Pulsar and ALOS 2 satellites. Like I say, the case study is for southern Africa, but this is a proof of concept for mapping the biomass and biomass change across the dry tropics where the method works well. I'm not going to give an introduction to radar remote sensing other than to say it's an active remote sensing method. So the satellite sends out its own energy at a characteristic wavelength. The energy comes down, it interacts with the land surface, and then depending on what's on the land surface, some of it comes back to the satellite. Wonderfully, and not coincidentally, the characteristic wavelength of ALOS interacts really nicely with tree branches and tree trunks. So the more branches, the more trunks you have, the more of the energy comes back to the sensor. And that's what we're measuring. When I say backscatter, that's the amount of energy coming back to the sensor. It sees through clouds, it sees through smoke, it works day or night, although it needs quite a lot of energy. It comes with other problems, but it does get around some of the problems associated with optical remote sensing in these systems. It ignores the grass, for instance, which isn't at the right size. So what do I mean by deforestation, degradation, and regrowth? So with a kind of red plus goggles on, deforestation is when you go from a forest state to a non-forest state. This is a savanna, so there's not really any forest, but we have to kind of shoehorn that terminology into the discussions about management in these landscapes. So you might call it a woody threshold of about 10 tons of carbon, roughly represents 10% canopy cover. If you cross that line between two dates, that's deforestation. If you lose biomass but don't cross that line, that's what in red plus terms you would call degradation. It doesn't always mean that the ecosystem isn't useful or productive, but that's from a carbon perspective anyway, degradation. Then regrowth is anything where the biomass is going up and it was a forest in inverted commas to start with. To jump straight to the results, here's a biomass map of the region. So Mozambique, to Tanzania on the east. The actual product is at 25-meter resolution. The map here is at 1 kilometer, but you can see a kind of pattern of lower biomass stocks in the south, higher biomass in the north, where it's a bit wetter. But the more exciting result is the biomass change that you can see initially over just a 3-year period. Red represents areas losing biomass, green represents areas gaining biomass, and you can see large losses along the, is that button going to do the trick? Yeah, large losses along the eastern seaboard near a lot of the big ports and the big cities, and same around some of the big cities in Angola. A particular hotspot of biomass in the very densely populated areas in southern Malawi. But you also see lots of green on this map. Green is increasing biomass. Pretty much everywhere where the biomass isn't being chopped down, it's coming back, or it's growing, or it's increasing. And that's a really important takeaway from this. It's not actually a bad news story, I'm going to tell you. If we look in a bit more detail about the degradation story, well, degradation affects about 20% of the study area over the 3 years. So it's very, very widespread. And take-home message for the day, number one, that means it accounts for probably 2/3 of the biomass loss, and therefore the carbon emissions from the region. And it's mostly a feature of high biomass woodlands. The more woody bits of the landscape seem to be more prone to degradation. Deforestation, the numbers we get are substantially higher than existing products. The reason for that, we think, is that we pick up a lot more of what we call mopping up. So in already quite transformed landscapes, like the top one, these little red dots represent deforestation. So this is not the classic model of deforestation along roads with frontiers expanding into the savanna or the woodland. It's just tiny little pockets of trees in already quite transformed landscapes. And this method seems to pick those up in a way that the Hansen product, for instance, does not. And actually, that's the dominant mode of deforestation in the region. It isn't this kind of almost Amazonian-style frontier deforestation along the roads. It's very small shifts in the tree cover across quite complicated landscapes. So this bit, you see the red dots, that's deforestation. The blue is degradation, and then the green, that little protected area, is increasing in biomass. So the background to all of this is probably a natural increase in biomass across the region. You can also see degradation in blue spreading out from the roads a bit further ahead of the deforestation, which makes sense in terms of how we think people utilize these landscapes. The regrowth term is huge, right? There's actually as much gain in biomass across this landscape as there is loss. They pretty much balance each other out as far as our method is able to determine. We see increases of about a ton of carbon a year. That matches with the in situ studies of regrowth rates. And it's not really a surprise. Like I said, it's a very resilient ecosystem. Trees love to grow back. It's quite productive. And there's been lots of disturbance in the past. So you would expect lots of areas to be increasing in biomass. But as I say, the net effect is that probably the whole system across the continent anyway is roughly in balance. So to start to wrap up, the bad news is that emissions are much higher than previous estimates, because if you include degradation, you get a much larger number, but also because we come up with higher numbers for the deforestation rate. If you crudely scale that up to all of the African woodlands, that makes the region a much bigger gross source than the Amazon, for instance. And that's largely because we're including degradation. I mean, you can see that bar there is substantially bigger than the red. But there's also a sink. The caveat, of course, is if you remember that map, the sink is mostly in the western bit of the region, the sparsely populated bits. The source, or the losses, are mostly on the eastern seaboard. So you can say it's kind of in balance, but actually in terms of the structure and functioning of these ecosystems, it's definitely not in balance. Implications, well, if you're thinking about REDD+ in the region, you probably need to think about degradation more so than deforestation. And there are almost no projects. There's one project I know of in the region working on forest degradation. Everyone else would much rather target frontier deforestation, which is probably the least prevalent mechanism of biomass loss. Now, I've got 1 minute left, so I'm going to sneak ahead. Since I wrote the abstract for this talk, we've been looking at the patterns of loss and trying to really understand some of the drivers. And I think I can fit it in my minute. This is a random forest regression, so essentially a nonlinear regression of the determinants of the biomass map. So what is it that predicts where high and low biomass is going to be? What you might expect, the more fire you have, so number of fires, the less biomass you have in your landscape. Makes sense. The more rainfall, the more biomass. Okay, these are the ecological determinants of the structure of the continental scale landscape. But look at the people ones, right? This is what we were very interested in. Here's human population density. This is rural population. Not really any strong relationship, perhaps a slight increase in biomass with increasing population density. And that really speaks to our idea that people in these landscapes cultivate and maintain forest resources very carefully. If you think back to Fairhead and Leach and those kind of arguments, that's what you can see in that figure. Distance to city, however, is associated with a decrease in biomass. So the closer you are to a city, the less biomass there is in the landscape. And given that most of the cities run on wood fuel, huge charcoal industry in the region, it's probably the fourth biggest industry in the region, it's not surprising that you see that and you see the deforestation and degradation spreading out along the main roads from the urban areas. So the other take-home really is that the patterns that we see are really strongly suggest that that cities have a major role in shaping the ecology of this landscape, much more so than rural livelihoods. Thank you for your attention, and please have a look at the paper if you want any of the details of the methods, and also the open source tools so you can replicate the method at your study site. The data's all free and open, and the tools are open too. Thank you. Thanks.
So any questions?
Curious, what is the sort of precision you can get to confidently detect the change with the degradation biomass?
So it's a probabilistic method. So we just give a probability that the pixel has either been deforested, degraded, or is increasing in biomass. And you can choose to deal with those probabilistic outcomes as you wish. You could categorize them and say, I only want the ones that are 95% sure that they've undergone that transition. But we use the probability to weight the biomass change that we observe. So if it's kind of a 50% chance that it's been deforested, we count the biomass change as 50% when adding up the total for the deforestation emissions.
So, thanks. I really enjoyed this paper, especially because you began by qualifying that degradation is defined only in terms of carbon.
Yes.
So that I felt there's a commonality between that question and the previous speaker's definition of degradation. I feel that if you want to define degradation in a particular way, you might start off by saying degradation is a social construct.
Yes.
And so therefore not use the term at all.
Mm-hmm.
And so maybe you should just say decline in carbon.
Sure.
And just not use the term because the term is very loaded. People might be, reducing. I mean, the Indian case of savannas being covered with invasive prosopis,
Yeah.
you see a lovely increase in biomass and carbon at
Yeah.
the cost of grazing pastures, right? So
Mm-hmm.
you might not want to use that very loaded term.
Yeah, I'm totally with you. A little bit of the political ecologist inside me dies every time I call that degradation. But from the social perspective of someone at a global scale trying to manage carbon emissions, it is degradation. We may not think that's the appropriate frame. But yes, I could call it over-harvesting or biomass loss. It would be less loaded.
Shown map about the rate of degradation in some regions of Africa. Did you include also a little bit of ground data? Because sometimes, especially when you're using those satellite data, you make maybe pixel effects that may exaggerate. You can see the area is highly forested or it's not forested. How do you handle that?
So yeah, the method is a fusion of the radar data with quite a lot of ground data. So the ground data is used to calibrate the radar sensor so it can measure biomass, but also in the validation. So we have a data set where we know degradation has or has not occurred, where we know biomass has been increasing as well. Of course, the spatial data, the ground data is quite limited in its spatial extent. It mostly comes from Mozambique and Tanzania, where I've worked most. We don't have a continent-wide validation data set yet, although if you're interested in that, there is a network forming to try and create such a thing.
So as a follow-up question, would that be one of the limitations of like using your open source tool if you want to apply it to other regions that you might not have the validation data?
So the biomass backscatter relationship, so between the woody biomass on the ground and what the satellite sees, appears to be quite constant across that region. But I've chosen a fairly ecologically homogeneous, that's why working in the largest savanna in the world is good, because it's the structure of it is relatively similar all the way from Angola to Tanzania. If you went to a system where the stem size distributions were different or things like that, you would want your own ground data to calibrate the biomass mapping.
Quick questions.
Yeah, to talk about the biomass backscatter relationship, what do you use as a backscatter relation? Do you use tree height? Do you use structure, vertical structure? What kind of information do you extract from the air band?
So it's just a correlation between the average backscatter of the pixels that make up the plot and then the biomass as measured by measuring dBH and using an allometry to estimate woody biomass. Yes, totally. Yeah. I mean, it's based on a physical model of the shape of the expected relationship, but it's an empirically calibrated model, a water cloud model.
Thank you, very interesting.
Thank you. What's the magic here?
Yeah, it's sort of...
Thank you.
Yes, I think something like this.
How does it work? Okay, good afternoon everybody. I'm very happy to be here. My name is Teresa De Marzo and I'm a PhD student in the Humboldt University of Berlin and in the Catholic University of Louvain-la-Neuve. I will present today my work about, regarding relationship among forest disturbances, land use and woody cover patterns. It is an approach to forest degradation assessment in tropical dry forest. Why are we interested in forest degradation in tropical dry forest? Well, tropical dry forests are of great importance for their critical role in climate regulation and because they harbor a unique biodiversity, and also they provide ecosystem services that sustain the livelihood of many people, including the world's poorest one. However, tropical dry forests are under great pressure. And they are fastly disappearing with the deforestation rates that are by now even higher than moist forests. However, apart from what is lost, the remaining forest is often affected by extensive forest degradation, as we already heard. That is often overlooked and about which we know very little, mainly because of lack of method to monitor it. A very good example for this is the dry Chaco. The dry Chaco is a tropical dry forest, the largest remaining continuous tropical dry forest. It extends mainly in Argentina and a bit in Bolivia and Paraguay. My study area is the Argentinian part of it. When we look at the dry Chaco from satellite, we see this kind of image. So large part of the forest is lost, mainly for conversion to cropland. However, if we then focus on what is left of the forest, we see that this is also, hope it's possible to see, is also highly degraded. However, while we know quite a lot about the deforestation in the Chaco, like rates and how it worked, we really know little about the degradation. So this is what motivated my research, and my first attempt was to try to understand which are the land use practices that leads to forest degradation in the Chaco. So I reviewed the literature to understand this. What you see here in these photos, both from the ground perspective and from a satellite perspective, it's a puesto. This is, puestos are homestead in the forest where generally one family lives, and the family lives out of small-scale cattle ranching, mainly cows and goats. The cattle is left free to graze in the forest, and the pressure of the overgrazing in the forest is reported to be one of the causes of forest degradation. Selective logging is also a land use practice very common in the Chaco. This can be either for charcoal production. What you see in the first photo is our ovens to produce charcoal, and this is the effect that has the harvesting of wood for charcoal production on forest. Here it's difficult to see, but it's one of those ovens. Selective logging is also related to the extraction of economically valuable species. Fire, or better, the change in natural regimes of fire are also reported to be one of the causes of forest degradation. And then we are also curious to understand if the highly intensive management practice of these large fields that are substituting the forest are also affecting what is left of the forest, so the forest close to fields. I use this information to to conceptualize what are the pathways of forest degradation in the Chaco. So here you see the 4 land use practices that I listed before. And in this graph, you can see both what is the short-term effect of those practices on the forest, but also what is the output on a longer term in terms of forest structure. And what was interesting to understand is that many of those pathways leads to a forest that gets more homogeneous, with less big trees and more shrubs. Therefore, to understand forest degradation in the Chaco in its complexity, we, on one side, need to understand the current patterns of tree and shrubs, so forest structure. And on the other side, we need to understand which are the forest change that led to the current situation. So I'm going to continue talking about this second point, monitoring forest changes in the Chaco. We decided to use Landsat. This is a very well-established algorithm of time series segmentation. What you can see here as an example is the time series from a pixel where I could see that there was, these are very high resolution images from Google Earth, while the time series is of Landsat images. It's a time series of tassel cap wetness data, and you can see that the land trend fit, that is the blue line, can capture the even subtle change of selective logging. From the segmentation, from the land trend result, is it possible to extract metrics that describe the disturbance, for example, the magnitude of it, or the duration, in this case is just 1 year, or the year when this happened. And those information can be used to then map the disturbances. So here again we have an example of selective logging. Those are the little paths, very typical of selective logging, a skid path. And this is one of the metrics mapped for the pixel that exhibit disturbances. So here we see here of detection. And the information we can get is that in this case selective logging happened in many different years, so we can understand the special patterns. In this other map, we instead see the duration for every pixel, and then we can also understand more the temporal pattern in a way. So how long, like if those disturbances or the trends, how long they lasted. Then we can, of course, I mean, this is an example for a small plot, but we can use it for extend it to the full area. So with this, we, let's say, answer to the question, we can answer to the question which were the forest changes in the Chaco. And then, again, we want also to relate this to the the forest structure. To do this, we use a tree and shrub cover layers that that come from a work of Matthias Baumann et al. In 2018. And the interesting thing that we can, the interesting data that we can get from this is that some of the land use practice that we are interested in, they indeed have an effect on the structure. This is spatial. This is like spatial effect. So the distance from, for example, Puesto, that was the first picture we saw, shows that in general woody cover decreases coming closer to a Puesto. In particular, tree cover decreases very steeply, shrub cover less. Also, distance to cropland shows similar patterns, maybe as a result of, again, the herbicide spray drift. So to conclude, we are able to monitor spatial and temporal patterns of forest changes, both stand replacing and non-stand replacing disturbances, and this is, I think, pretty interesting. We can also capture subtle disturbances, for example, the one related to selective logging that are more tricky to monitor. We can also map the forest structure in terms of tree cover and shrub covers. So the next step for me is how, and the future work is how to relate these two to understand better the forest degradation in the Chaco. With this, I thank for your attention, and I'm open for questions.
Any questions? Yes, go ahead.
Thanks for your presentation. I was interested to know if you're thinking of having some measures of resilience or recovery of forest as well.
Yeah, I'm now not taking in account the recovery. It's of course something that it needs to be taken into account, and it's also a bit tricky because, of course, especially in a vegetation index, you can see recovery, but maybe what you are actually looking at is the recovery of shrubs. Then is actually what we define as degradation, so shrubs taking over the previous tree cover. But indeed, it's something that, with the right complexity, has to be taken care of. At the moment, I'm using only tassel cap wetness because it looks like the best performing one compared to, for example, other tassel cap components or NBR and DVI, not to talk about it, and EV. But yeah, I mean, there are interesting works on combining, for example, one of the last Cohen works on combining more than one index that might increase the accuracy of detection. I mean, no. Also, since my main focus is on what is still forest. I mean, so then the comparison with something that is more related to deforestation is, it's like I'm interested in understanding the disturbance inside the forest, what is still classifiable as forest. Did I answer you or not? Yeah. Okay, thanks. Sorry? Yes, let's talk later.
And I wonder how the metrics perform in the different parts of the chapter. Did you see like that? We often see that the time series analysis is much better in the higher stature forest, where the changes are more dramatic, and less good in the more open or lower stature stuff, where things are more easily confused. Do you see anything like that?
I still haven't addressed this thing. We are now working on building a timesync database that will also help us to understand better how the map performs in general. But yeah, I'm not sure now yet about this.
What is actually the reason for the selective logging? Is it specific trees, or is it just that they cut some and then hope it kind of comes back?
In case of the extraction of valuable species, is mostly this Quebracho colorado. That is, but it also a lot related to the charcoal production, and that is much less selective. I mean, there is a broader range of species that are burnt. Yes.
Okay, thank you very much.
This is,
Not sure. Okay. Thank you and good afternoon. So my talk is very different to what we have seen so far. I'm focusing much more on the climate impacts of land use or land cover changes and land management. And basically we are interested in that because often when we think about the climate impacts of land cover changes, we think of carbon sequestration and how that influences how the change in carbon dioxide concentration in the atmosphere changes the climate. But there's also so-called biogeophysical effects. So of course the land use changes alter the properties of the land surface. For example, there could be an increase or a decrease in albedo, which leads to more absorption of solar radiation, and so to a local warming. And in this case, or what I'm going to present now, we looked at how different forest management in Europe could potentially lead to a local cooling of climate, so that we can better understand if there is trade-off when we have forest management that should increase carbon sequestration, or if there's potential synergies. And the two data sets that are most important for me are from the Copernicus Land Monitoring Service. So they are called high-resolution forest layers. And on the left, you can see the tree cover density, which is defined as the area that is covered by forest canopy, basically in a 20-meter pixel. And I'm also using data about the broadleaf tree fraction, which gives me information which pixel is broadleaf forest and which is needleleaf forest. So I'm not sure if that's the best data available for Europe at the moment. Maybe you have some suggestions there. And now I'm linking this data to land surface temperature data. And basically here I'm using data from Severi sensor, so it's on board Meteosat, a geostationary satellite. So I'm having quite high temporal resolution, but a lower spatial resolution. And I'm also using land surface temperature data from MODIS. And I'm now trying to link the data on the forest structure that I just showed you and these land surface temperature in order to understand if there could be potentially a cooling if we replace needleleaf forest by broadleaf forest, or if there could be potentially cooling if we increase the tree cover density. And The results that I'm going to show here are basically produced using a multiple linear regression model, and I'm including some confounding factors like elevation and, for example, aspect or slope and other data. And I'm trying to do this analysis for different regions in Europe, so for the boreal region, continental, alpine, Atlantic and Mediterranean, in order to understand if this potential cooling effect from changes in forest structure differ over these regions. And first I'm going to show some results that are based on this on the Severi data, which is available on a high temporal resolution. So we were able to look at the diurnal cycle. And what you can see here in green is the potential cooling if we replace the needle-leaf forest by broadleaf forest. And in black you can see the potential cooling that would be caused if the tree cover density would be increased by 20%. And what is interesting here is that the cooling effect of increasing tree cover density is strongest at around noon, whereas the cooling effect of replacing needle-leaf trees by broadleaf trees seems to be particularly important in the afternoon and in the evenings. And we also compared these data to station observations in Switzerland, where we have observations of broadleaf sites and needle-leaf sites. And it seems quite consistent that we have a similar cycle, a daily cycle of cooling. So that was one of the first results, and we saw that there is basically what we can also see in this figure is during nighttime there is a warming, but during daytime there's a cooling effect. And we also wanted to know if this cooling effect could be particularly high if we have very hot temperatures, maybe like heat waves, or if there's no big difference. And what we could see is that if we look at the different temperature percentiles here, so at days when we have particularly hot temperatures and days when we have cooler temperatures, that in almost or pretty much in all regions we can see that this cooling effect seems to increase with higher temperature and is rather lower with when we have lower temperatures. So this was only for summer months what we looked at here. And what we can also see is that it seems that the cooling effect of replacing needle-leaf trees by broadleaf trees seems to be higher in the boreal region than the effect of increasing the tree cover density. And this seems to be the opposite in the Mediterranean, where the increasing tree cover density seems to be particularly important. However, I have to say that here in the Mediterranean, it's quite difficult to disentangle the effects from increasing broadleaf tree density and tree cover density, because from these two data sets that I'm using, there's a really strong correlation between the broadleaf density and the tree cover density. And so some of the next steps or ideas would be to really establish or try to have a closer link between forest management and the effects on temperatures. I think here these two spatial data sets from Copernicus Land that I'm using are rather showing like something about the forest structure, but not really about the management. And then I think it's important to better look into the nonlinear effects, because increasing tree cover density will at some point probably not make much difference anymore when the forests are already quite dense. And what we are also doing is having a closer look at the actual processes that influence the land surface temperature, like changes in albedo and evapotranspiration that go along with these land cover or land management changes. And as a conclusion, I would say that we could see that forest management or land management can have a strong influence on these local or regional temperatures, and that this effect is especially pronounced for hot temperatures. Then in addition, I think this looking at this diurnal cycle is maybe interesting. I haven't seen it much yet, but it could be relevant, for example, if we think of mitigating the urban heat island effect. So first, it's probably interesting that we should rather maybe have broadleaf trees in the city to better mitigate the urban heat island effect. And then it maybe makes a difference when this cooling effect is actually occurring, like for people who seek recreation, I guess. And which is very relevant for us. So I'm actually working at the Institute of Atmospheric and Climate Sciences, and there we always try to kind of validate and improve the climate models, and here it can give a lot of helpful information, I think. Thank you.
So, any questions about
Hi, great talk. Thank you very much. I'm just curious about one point you made towards the end of your talk about mitigating urban heat island. And I was interested to know your thought about, do you think an urban park with broadleaf trees would provide same kind of services as it would give in a natural forest setup? In a natural forest, a broadleaf forest.
Yeah.
The way it's providing cooling effect, do you think it would provide something similar when you have kind of an urban park surrounded by urban areas?
Yeah.
Because if it could, it would be really interesting to see the effect. And I was just wondering if you had any more thoughts into it.
Yeah, I think in the urban environment, the impact on humans is very obvious, and maybe if we have forests somewhere else, then it's maybe not anymore so much about humans, but rather about the ecological influences, I guess. Or there it is, I would say it's also important that of course these effects, these cooling effects, they can, to a certain degree at least, can cause a cooling to neighboring areas. I mean, through advection, and so then I think it's also relevant outside the urban areas probably. But yeah, that's a good question, I think.
Hi, this is really interesting. Thank you. I apologize if I didn't really follow. So, did you also have an idea of why they differ? So, is it water use efficiency, water availability?
Yeah. I think we still have to look a bit closer into it. I mean, what is kind of obvious is that the albedo is higher for broadleaf trees usually in summer, and then there's also more evapotranspiration, and it seems that especially this afternoon cooling effect that we see is probably related to stomatal conductance, I guess, could be something like that, but that's something we need to have a closer look at. Yeah.
So with the method you used, can it be applicable in other ecosystems, like in dryland areas?
Yeah, I think there are some studies that look also at global scale at the effects of land use and land cover changes, which may be interesting for you. I can later on mention them to you. We rather looked at the forest management. Yeah.
I think I have a final question is how local is the local effect? How can I imagine this sort of?
Yeah.
From when on do I start noticing this effect and when not? And is it meters, kilometers? I mean,
Yeah, it's a good question. I mean, I think in the urban areas, there's some studies about that, and it's rather meters. It's not, I think, I mean, and it depends. I mean, the effects can come regional. I mean, it also, to a certain degree, affects, for example, cloud cover and precipitation, and then it becomes more complicated. Yeah.
Yeah, because it triggered me a bit these studies about deforestation, for example, the Amazon, that you might then
Yeah.
have more or less rainfall associated with
Yeah,
it.
exactly. Yeah, that's something that we didn't really look into yet. That's probably, it's better to do this with climate models in most cases. Yeah. Mm-hmm.
Very interesting, thank you. So that was it for the full talks. We have 2 more flash talks of about 3-4 minutes.
Thank you, everybody. It's going to be flash, especially because I have only slept 2 hours in the past day. So very jet lag here. But anyways, I'm going to present you part of the work that we have been doing evaluating the payment for ecosystem services in Mexico. This has been a collaboration between the Duke University, University of Wisconsin, and the University of Maryland. And Mexico, as many other countries in the tropics, experienced very high deforestation rates during the 70s, 80s, and 90s. And as a response, the Mexican government implemented in 2003 a big, major payment for ecosystem services program that, in average, is giving economic incentives to the people of $31 per hectare. And it has grown so much that now more than 2.3 million hectares in the country has been benefited by this program, which accounts for more than 1%. And this is one of the biggest the biggest programs in the world. And if we want to monitor such a big program, we have 2 options. We go to the field, we measure trees, or we take and buy very expensive high-resolution satellite images. But these 2 methods are usually very expensive and not always available. So we look away and start looking in satellite images, and even better, some work that already some people did for us globally, so we can extract information out of that. So we use the Global Forest Change product produced in 2003, which was perfect because it accounted for areas since 2000 before our program and after the program, so we can start seeing differences, not only in the forest, from bottom, not only in the current forested areas, but also how they have changed every year. So what we did was using this forest cover product and translated that into a forest composition and forest configuration categories, so we can extract more information out of that forest, instead of just measuring how much deforestation, saying, well, we have patterns of forest ages, forest interior, forest perforation, that can give us more ecological meaning for these effects of the program. We did that for 2 dates, 2000 before the program, 2012, and start recording different events, like the one that we are highlighting here, where we see that the forest interior has been fragmented by the creation of different roads, or where the forest interior has completely replaced in many areas, leaving space to many isolated areas of forest patches, or the creation of roads that created perforation in forest interior. So we did that analysis for the whole country at 2 different times, and start summarizing the patterns. So this is what we found. This is very partial results. So in the whole country, most of the changes in forest core, or what we call forest interior, happen in the Yucatan Peninsula, southern Mexico, and along the Gulf of the country. It's mostly where the poverty area, the poor areas of the country are, and also where the tropical forest ecosystems are more prevalent. Then we did a matching analysis to see the effects of the program, comparing what is the propensity of areas that are receiving the money and similar areas that have similar geographical and economical characteristics and making this comparison. Here we have areas in blue that didn't receive payments, areas that receive payments. Here we divided the country north, central, southeast, southwest, and southeast. and different forest morphology characteristics and forest fragmentations. Most of the changes in forest core or forest interior, what we call it, happen towards the south of the country. Not so much changes we see happening in the north, but in the south there were more. However, what is interesting is that in the southeast and southwest, the changes that we are observing in areas that receive payments are only half as much as areas that don't receive payments. And remember, those are matches areas, so they have the same propensity to develop changes. So the same way, the areas that, how big the deforestation patches were, they were twice as big. In average, were 3 or 4 hectares areas that were receiving payments and 6 in areas that didn't receive payments. And also the creation of more forest patches, twice as much in areas that didn't receive payments. There is a much more different forest fragmentation categories that you can check in our recent publication out last year. But in conclusion, we found that the PES limited, however, didn't stop the forest fragmentation. And the program actually works better in the south. So our suggestion is for the program managers to target those areas. People in the north, despite of the program, are not touching much of the forest. So if we have those resources and they are not making much impact in the north, let's transfer those to the south. And we are happy that easy and to obtain global forest change data is globally available, can be useful to monitor different forest protection incentives and actually measure the impact of them in the ground. So with that, it was very flash talk. Sorry for not including more details, but thank you for talking, and I might take questions.
You have ample time for some questions, so any takers?
Yeah.
I was wondering if you compare your results when they, with maps of deforestation, just how you compare, like, when you have payment for environmental services, they actually will make the data set that they have with us against the deforestation.
Sorry, I didn't hear it, sorry.
So I was wondering if you actually compare your results of fragmentation with data on just deforestation.
Yes, so those, they are very related to each other. If there is deforestation, very likely there will be fragmentation. However, sometimes deforestation happens, like they were describing it, that is close to the roads, and at the edge, deforestation keeps advancing towards the edge of the forest. However, we wanted to capture events of selective logging or something that was happening in the interior that is not easily detectable, like in deforestation analysis. Something very cool that we saw is that we accounted for 3% of forest lost in the country, but that translated in 9% of forest loss interior, of loss of forest interior. So even though that we only have 3% of deforestation, we lost 9% of the forest interior. This is how they're useful for measuring fragmentation. Yeah.
I have a question about the new forest that is coming up thanks to this program. Have you examined the structure? So is it filling up holes in the previous forest? Is it new areas that are becoming afforested, or?
We only measure forest loss in this analysis, so we are not measuring the forest regeneration for this, because the events are very, very slowly, so they were almost negligible in our study area. So
you don't have it on the Hansen?
Yeah, because we don't have it on the Hansen data.
So I have a final question. So you showed these different characteristics of this, where you have a past program and where you don't have one. Did you also look at total forest loss?
Yes.
Oh, sorry, I might have missed that.
Oh, that was the 3%.
Oh, okay, that was
3% of forest loss in the 12 years that we analyzed.
So, and one thing that we also had a bit of a problem with this REP plus performance is the matching of your intervention and control.
Yes.
And you said you use geographic and socioeconomic.
The socioeconomic characteristics were mostly distance to markets, distance to roads, and distance to cities. Those are the ones that we collected socioeconomic. However, we try to account for income by dividing the country in different socioeconomic areas, areas that are more wealthy in the north, areas that are poorer in the south. So that was our way, because we didn't quite have a way to control for economic, like individual properties, income, or something like that.
But did you also match them on how the deforestation looked already in the beginning? Whether there also was already more or less fragmentation? Was there some matching based on those characteristics already?
Our matching was set on variables or properties that have at least 80% of initial forests in the year 2000. So our baseline, we only selected those areas that at least have 80% of forest cover. Yeah.
Thank you very much.
You do that? I don't know how to. I don't want to break it.
Don't worry. Sorry. Feels like the Olympics. Hello everyone, and thanks for holding on to the last talk. My name is Matteo Jucker. I work in the University of Applied Science, and I'm here to talk about a tool we developed to monitor dry rangelands. So we are going to quite a different environment and also quite a different scale compared to the studies that were proposed before. We know how difficult it is to actually change the management of a certain ecosystem. And especially if this ecosystem looks like that. This is our grassland, and this is our forest in the central east of Morocco. And so we thought, instead of looking on how we can use local knowledge or stakeholder to, let's say, understand better the environment, which is something that is important, but it's mostly important for us. We try to think of how can scientists actually support participatory management in those areas. And lucky for our ego and for our employment, there's a consistent lack of up-to-date spatial information on degradation of ecosystem. This is something that is comparable in Morocco as it is in Spain or Italy or Greece. And sometimes actually you discover that places you would think more advanced have even less information than others. We know that the critical point is the knowledge co-production, so the interaction between land managers and land users, stakeholders in general, and science. And so what we figure out is not to have a precise scope of the project, but actually have more of a process that is influenced by the demands of stakeholder through an iterative process. We are around the third iteration of this. The core of our method is to provide context-specific and dynamic information for rangeland. And this is obtained primarily by considering the landscape. In dry areas, the landscape, so the aspect, the slope, the type of land cover influences the productivity of the pasture, or in general what we can see in terms of vegetation from the NDVI. So the first thing was define this very patchy map of different landscape units. And that allows us to pass from this, which is the simple NDVI. It has been translated into biomass in kilos per 10 square meters, but is the simple NDVI. We can pass from this to highlighting a certain landscape unit, observing the variance in the distribution of NDVI within this landscape unit and categorizing it in very degraded to potential areas. We repeat this for all the landscape units in the area, and we obtain quite a different picture. especially what is important is not only what are the degraded places, but what are the potential places or the places that we consider are the best situation. These are important because they give a very good reference, not only in quantitative term for us to measure degradation and changes, but also to the local people. We can tell them, go there, look at how it is, this could be your land, or potentially this could be your land. Moreover, this approach makes it very easy to integrate data from coming from stakeholder knowledge. For example, here on the x-axis, we have the grazing intensity obtained through participatory mapping, and on the y-axis, we have the vegetation as estimated from satellite images from Sentinel and Landsat in this case, and we identified different groups, different type of pastures that have different problems and different dynamics. Finally, the last point is the dissemination. In the last 1 to 2 years, there have been a growing number of ways that allows us to disseminate very easily on the web what we do on our satellite images. This is a screenshot because, you know, they never work the day of the conference. But this is the very interesting part. And what has been very beneficial is sending out the maps almost as soon as possible. So as soon as we have something interesting, making sure that the information is not considered as a final. But there are many points that are still open on this. So how to communicate to non-literates, can we go beyond graphs, and what other formats beyond map, how can we disseminate this information to people that don't have access to Google every day. That's it. Thanks for listening.